Hi students, 12th standard chemistry, unit 5, coordination chemistry. So in this session I am going to teach you the book back question. So we have already seen the examples for valence bond theory. So it is the 23rd question in your book back. Okay, what they are asking? They are asking us to find out the nature of bonding in this complex. Okay, for that I am going to do all these steps. So first step is the atomic number. What is the atomic number of the central metal atom here? The central metal atom is Gopal. The atomic number of Gopal is 27. Then I have to find out the oxidation state. Okay, how to find out the oxidation state, that you know very well. So I am writing the complex here. So this is our complex. I am going to find out the oxidation state for this, okay, for the central metal atom. So I am keeping this as X and plus 3 into the oxidation number of this oxalate ion is minus 2 equal to minus 3. So what will be the answer that I will get? Minus 3. So X is equal to plus 3. So what is the oxidation state of the Gopal here? It is in plus 3 oxidation state. Then the next step, I have to write the electronic configuration for the central metal atom. What is the central metal atom? Gopal. The atomic number is 27. If you know the atomic number only, then only you can able to write the electronic configuration for any element. Let me write the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Okay, if you add these numbers you will get the number 27. Okay, this is the electronic configuration for the central metal atom Gopal. In this case I have to take the outermost valence electron. Okay, the Gopal is having the plus 3 oxidation state. What is the outermost electronic configuration? 4s2, 3d7. Okay, if it is plus 3 means I have to remove 3 electrons from the outermost electronic configuration. So if I remove the 3 electrons from outermost electronic configuration, what is the thing that I will get? 2 electrons removed from the s orbital and 1 electron will be removed from d orbital. So at last I will get 3d6, 4s0. Okay, so for the Gopal it is having the plus 3 oxidation state. The outermost electronic configuration is 3d6, 4s0. Okay, then the next step is outer orbital of a metal. Okay, I am going to draw the degeneracy set. 3d6, d orbital is having 5 degeneracy set. Then the s orbital, then the p orbital. Okay, so this is having 3d6 electron. In the 4s orbital there is no electron, so I am writing 0 here. The same way 4p orbital also not having any electrons. So let me fill the electrons. We have to fill the electrons according to the Hoffa principle. Okay, so 6 electrons are there. So let me filling the electrons. 1, 2, 3, 4, 5, 6. Okay, so this is the outer orbital of a metal. Then the next one is nature of the ligand. So we have to find out the nature of the ligand, whether the ligand is weak field ligand or strong field ligand. Our ligand is C2O4, which is nothing but oxalate 2. So this is the compound C2O4. It is having 2 donor atoms. It is having how many donor atoms? 2 donor atom. Oxygen is the donor atom here. So this will comes under weak field ligand. So what is the next step? Outer orbital of central metal atom in the presence of ligand. What the ligand will do? The ligand, if the ligand is weak field ligand, there won't be pairing taking place. Okay, if it is strong field, the pairing will be taking place. Since we are having the weak field ligand, the 3d orbital will be I will be writing as it is. So then the next one is s orbital, then p orbital. Okay, so I am going to fill the electrons as it is. 1, 2, 3, 4, 5, 6 electrons. Then 4s orbital is empty and 4p orbital is also empty. And here we are having, so our ligand contain three number of ligands we are having, but this ligand is having 2 donor atoms. So 3 into 2 will be having 6 ligands. Okay, if it is possessing the 6 ligands, we need 6 vacant orbitals to form the bond between the metal atom and the ligand. Okay, so for that I am writing the d orbital here. So I need 6 vacant orbital. 1, 2, 3, 4, 5, 6. Let me write the hybridized orbital. Hybridization, which is nothing but the mixing of atomic orbitals. Okay, so I am going to write the 3d6 orbital as it is. 1, 2, 3, 4, 5, 6. This is 3d6. I am going to mix 1 4s orbital. This is 4s orbital and this is 4p orbital, and I am going to write 2, 3, 4, 5 and d orbital. 4d orbital. Here in this case I am going to take this s and these 3p and these 2d. Okay, so let me write here. Okay, so these 6 ligands will donate a pair of electrons towards the central metal atom. 6 ligand in the sense, one oxalate ion contains 2 donor atom. So the electrons will be donated to the vacant orbitals or the central metal atom. So we are getting the pair of electrons. So this is called the hybridized orbital. Okay, 1 s orbital from 4s and 3p orbital from 4p and 2d orbital from 4d I am taking. So the hybridization is sp3d2 hybridization. Okay, what is the coordination number here? If there is a presence of 6 ligands, the coordination number will be 6, or otherwise if there is a how many donor atoms are there. Okay, here 6 number of donor atoms are here, so the coordination number will be 6. What is the hybridization? The hybridization will be sp3d2. Okay, so in this case, in this hybridization, outer d orbital taking part. Okay, outer d orbital taking part. So this is also called outer orbital complex. This is also called outer orbital complex. Then the next one is geometry. Okay, if the number of ligand is 6 means, and also sp3d2 as well as d2sp3 means, what is the geometry that you will get? We will get octahedral. Then the magnetic property, If the complex is having the unpaired electron, that is said to be the paramagnetic. See, our complexes contain unpaired electrons. So, this is having 4 unpaired electrons. So, this compound exhibits paramagnetism. Okay. So, the last one is magnetic moment. How to find out the magnetic moment? By using the formula mu is equal to square root of n into n plus 2. Okay. What does n indicate? The number of unpaired electrons. How many number of unpaired electrons are here? 4. So, 4 into 4 plus 2. So, 4 into 6. So, if you do the simple calculation, what is the answer that you will get? 4.89 Bohr magneton. Okay. If the number of unpaired electron is 4 means the value also will be come in 4 only. Okay. So, this is the nature of bonding in this complex. Okay. Hope this is clear to everyone. Thank you.